Welcome. So if you're dealing with anything like quality control, risk assessment, or really any situation with small, finite groups, you absolutely need the right tool in your kit. Today, we're going to unpack a really powerful one, the hypergeometric distribution. Don't think of this as some dry academic concept. Think of it as a precision instrument for making smart calls when every single item, well, it counts. Okay, let's get right into it. Here's our game plan. We'll kick things off with the what and why. Then we'll draw a really important line in the sand between this and another common model. After that, we'll break down how it actually works, walk through a real-world example, and then wrap up with the key takeaways you can use. Let's go.
All right, section 1. We're doing this classic consultant style, which means we're starting with the answer first, the bottom line up front. I'm not going to make you wait till the end. I'm giving you the core definition right now, so everything else we talk about will just click into place.
Okay, the two words on this slide that change everything are without replacement. Seriously, lock that phrase in. Imagine you're dealing a hand of poker. When you pull an ace from the deck, you don't put it back in, right? Of course not. The deck itself, your whole world of possibilities, has now fundamentally changed for the next card. That is the exact scenario this distribution was built for. It's for when each thing you pick affects the odds of what you'll pick next. It's a model built for reality.
Now, this brings us to a super common point of confusion. A lot of people just default to using the binomial distribution, but for the kind of small batch problems we care about, that can be a huge mistake. So let's make this distinction crystal clear.
This slide lays it all out, side by side. It's like two different universes. On one side, you've got the binomial world. Think of a giant gumball machine with millions of gumballs. Taking one out doesn't really change the odds of getting a red one next time. The trials are independent. But then, you've got our world, the hypergeometric world. Here, you're drawing from a small jar of marbles. You take one out, and you don't put it back. You bet the odds have changed for the next draw. The trials are dependent, and that dependency is everything. It's why this tool is so important.
Okay, section 3, the core mechanics. Let's get under the hood and see exactly how this thing works. We're going to look at its basic properties and the key assumptions you need to have in place to use it right.
So these are the fundamental rules of the hypergeometric world. First, it's a discrete distribution. That just means you can find 2 defective parts, or 3, but you can't find 2.5. Second, as we've been saying, the probability changes every single time you make a draw because the trials are dependent. And finally, its behavior is driven by a few key numbers, which we're about to define. These are the rules of the road.
Now, for the fine print, the assumptions. To get the best results from this model, a couple of things need to be true. You know, the total population and the number of successes and failures within it should be quite a bit bigger than the sample you're taking. This just makes sure that your sample is actually telling you something meaningful without, using up the whole batch. These aren't just technical details. They're the guardrails that tell you when this is the right tool for the job.
Okay, before we throw the formula up here, let's just clearly define the pieces of the puzzle. This is super important. N is your total population, every single item you've got. D is the total number of successes in that group, like how many defective items there are in total. M is your sample size, how many you're actually going to check. And R is the magic number. It's a specific outcome you want to find the probability for. Like, what are the odds of finding exactly 2 defective parts? And here is how it all comes together. I know, it might look a little intimidating, but it's actually super logical. That C just stands for combinations. It's just a way of counting how many ways you can choose things when order doesn't matter. So the top part is just the number of ways to pick the successes you want times the number of ways to pick the failures that are left. And the bottom, that's just the total number of ways you could have possibly picked any sample. So really, it's just the outcomes you want divided by all the possible outcomes. That's it.
All right, enough with the theory. Let's make this real. A practical example is where the rubber really meets the road. We're going to take all these abstract ideas and make them totally tangible in a classic quality control problem.
So here's our scenario. It's a perfect fit, right? We've got a small, finite population of 100. We're sampling without replacement. This is the exact kind of question a plant manager has to answer every single day, where a bad batch could be really costly, and getting the probability right is absolutely essential.
So first step is always to structure the problem. We just map the story to our variables. Total population, N, is 100 bearings. The total number of successes, which in this case are defective bearings, D, is 30. Our sample size, N, is 3. And the specific result we're testing for, R, is finding exactly 3 defectives. Boom! All our inputs are ready to go. Now, before we get the final answer, it's really helpful to calculate the mean, or what we'd expect to see. And for this problem, it's 0.9. What this tells us is that if we did this test over and over and over, on average, we'd find just under one defective bearing in each sample of 3. It's a great way to get a feel for the landscape. And here we go, the main event. What's the probability of our original question? When you plug those numbers into the formula, you find out that the probability of drawing exactly 3 defective bearings is about 2.5%. So, not super likely, but definitely not impossible. And now, that plant manager has a hard number to work with. They're not guessing anymore, they're quantifying risk. And that is the whole point. So, we've done all this analysis. What's the so what? Section 5 is all about boiling this down to the core strategic insight. This is the stuff you need to remember and actually use. So here's the bottom line. The hypergeometric distribution isn't just another formula on a stat sheet. It is your go-to model for any situation where you're picking from a finite pool and you don't put things back. Think quality control, polling small groups, genetic analysis, heck, even figuring out your odds in a card game. It's the tool you grab when the very act of looking at something changes the system you're looking at. And that brings us to the end. So I'll leave you with this question. You now have a very specific, very powerful tool for a common type of problem. So think about your own world, your job, your research, even a strategic decision with a limited number of choices. Where can you apply this lens to get a clearer, more accurate picture of what might happen?